Hey everyone, welcome back to our Fortran Bootcamp series. This video is going to be a little different. This is kind of a probably one of the first in a set of bonus videos that I'm going to be creating, where I'm not talking so much about inherently programming in Fortran as understanding some modules that have been created and how you can use those in Fortran. So this specific module we're going to be looking at today is a set of linear algebra subroutines and functions. Now the specific file that I'm looking at here, and I'll post a link to it in the description for the video, is contained within the MachLine package. MachLine is a supersonic panel method that we've been developing as part of our lab, and this is all of the This file contains all of the linear algebra routines that we use within MachLine. But it's totally available, and if you're watching this from outside the lab, you're more than welcome to jump onto our GitHub page, steal this file, and use it however you'd like. I will mention that this is definitely not the end-all be-all solution for linear algebra in Fortran. In fact, if you're really looking for high performance linear algebra routines, you want to take a look at LPACK. That's a professionally developed linear algebra package, and it takes advantage of specific computer architecture to be able to perform linear algebra functions really, really quickly. You'll notice in this video some of these subroutines that we're looking at do take advantage of parallel processing using the OpenMP library, but that's about it as far as optimization goes here. But anyway, I hope this is a useful introduction to how some of these subroutines work, as well as giving you an idea of more of what does real Fortran code look like. This is something that I've not created as a demo. This is something that is really being used as part of a larger software package, and so you can get a better idea of what things look like. So let's dive right in. In this module, you'll see we don't have any types defined. All we're saying is implicit none, and then we go straight to contain, so we're not creating any user-defined types as part of this module. We jump right into our subroutines. The first subroutine that we've got here is mat_in, but what this does is inverts a matrix. And what it's asking for is n, which is the size of the matrix to be inverted. Obviously your matrix has to be square. We can't invert non-square matrices. Well, you can using pseudo-inverses, but that's something else entirely. Anyway, so n is the size of the matrix we want to invert, A is the matrix that we actually want to invert, and AI is the inverse of that matrix. And this subroutine so what you have to do is you have to give it space for putting in the inverse of the matrix that you want. So before you call this subroutine, you need to make sure that you have a matrix defined in your main program that is allocated and has the space to hold the inverse of the matrix that you want. You'll notice it has to be allocated because of how it's specified here. So you can see in the input, it's looking for A to be an n by n matrix and AI to be an n by n matrix. And notice there's nothing here saying allocatable, no implied dimension here, and so whatever you're passing in already has to be allocated, whether you've declared that as allocatable or you've explicitly stated its size at compile time, doesn't really matter, but that needs to be taken care of beforehand. And then it will run through and it will perform all the necessary calculations for inverting that matrix. I won't get into the nitty-gritty details about that. You can go read a linear algebra textbook for that. I will just point out though that inverting a matrix is a numerically unstable operation, and so you should avoid it if you can. Now if you're working with really small matrices within MachLine, I invert 3x3, 6x6 matrices all the time, just because that's a small enough matrix that the numerical instability isn't a huge issue. But if I were to use that, say, for solving my system of linear equations, where I'm solving a system that's 20,000 by 20,000, that inversion can really become an issue, and so we avoid that. We use other methods for solving that system of equations, which we'll talk about now. One of the most common ways to do that is using LU decomposition, and that's what this subroutine does, LU solve. Again, what you're doing is you're passing in the size of the system that you're dealing with. So n tells it, one, the size of A, so A is an n by n matrix, and then B is your length n vector. So this is solving the equation AX is equal to B. And then, since this is a subroutine, we're also giving it a space for putting out our solution vector. Now this subroutine is declared a little differently than the one up above. You'll notice that where X is declared, it's a real implied dimension, allocatable, and so you don't have to allocate X before passing it into this function. In fact, even if you do, Fortran will go ahead and wipe that allocation because the intent here is specified as out. You'll notice that the intent for B is in, so it's not going to change B, but it will change A. Part of what LU decomposition does is it decomposes your A matrix into two separate matrices, a lower triangular matrix and an upper triangular matrix. And so you can actually replace A in place with its LU decomposition. And that's what's happening here. So that's why A is specified with intent in out. And so once you've called this subroutine, A is no longer the A it was before. So if you need to be able to call this subroutine and then use A again later, really make sure that you've made a copy of A, because again, this subroutine modifies A, and you won't get it back. But basically what LU solve consists of is a decomposition into LU form, and then it will perform back substitution to actually solve the system of equations. This is the expensive part. Computing the decomposition is order n cubed, whereas back substitution is just order n squared. And so if you're solving a system of equations multiple times where B is changing, you can actually keep the decomposition of A the same, because if A isn't changing, its decomposition isn't changing. And you can just call this LU decomp once, and you can do the back substitution a whole bunch of different times. This LU solve won't do that. You'd have to do that manually using these two subroutines, but it's pretty straightforward. And those are defined here, LU decomp, and then LU back sub here. This subroutine is included in here just because it uses this LU solve subroutine, but this, if you hand it a list of 3 points in 2 dimensions, then it will fit a parabola to that and give you the coefficients for it, which is kind of nice. There's a subroutine in here called decompose blocks, and I won't talk about that right now, but you'll see where it's used here. So there's a subroutine for performing block SSOR solve. SSOR is symmetric successive over relaxation. This is again solving a linear system of equations, AX equals B, but it does so iteratively, and this is a really popular method in the CFD world because it's a lot more efficient for sparse matrices. Now this subroutine is implemented here, does nothing to assume sparse matrices, it's assuming dense matrices. And that's one of the reasons for using the block version. Using the block version also makes it behave better when we don't have a diagonally dominant system. And you can tweak that by setting, what the block size is. Tall tells you your convergence tolerance. Once we've dropped below that, we can end the iteration. There's a whole bunch more arguments to this one here. Block Jacobi is a similar solver. The nice thing about block Jacobi is that it is easily implemented in parallel. And so if you're really looking for speed and you want to use an iterative solver, you can use block Jacobi. Make sure you're using OpenMP, and it can get you a solution really, really fast. It's not guaranteed to converge, but if you're willing to play with it and tweak your block size and your relaxation parameter, then you can get it to converge. I'm not saying it's not likely to converge. It is likely to converge, but convergence is not guaranteed. And you can play with these settings to make it converge really quite fast. So that's a good solver to use. We also have Purcell's method implemented here. You'll notice pretty much all of these have the same structure of arguments. You're putting in the size of the system, putting in your square system matrix, your right-hand side vector, and then space for your solution vector. These iterative ones are different because we've got all these other arguments that you can pass in, and those are explained here. And then your solution vector, I've kept it so the solution vector is always the very last argument. That just makes sense in my mind. Anyway, Purcell solve, very similar to LU decomposition. It's an order n cubed direct solver. Works really well, but is slow. Then we get into some interesting ones that we've developed for specifically for MachLine, get lower bandwidth, get givens rotation. These are all used for, let's see, I guess this is where we are. These are all used for a subroutine called QR given solve UP. This is the QR UP or QR upper pentagonal solver. So in supersonic flow, we get a system matrix, or our AIC matrix is what we call upper pentagonal. So there's some subdiagonal for which all the elements below that are identically 0. We can use that to speed up the solving process somewhat using QR decomposition via givens rotations, and that's all implemented here. There's a fast version of that using fast givens rotations. Those are implemented in this subroutine. And that's all in this subroutine here. So this does essentially the same thing as the one we saw up above. The difference is this is using fast givens rotations. The other one was using standard givens rotations. And then we also have the GMRes solver implemented. Now GMRes is another iterative solver. It's really cool. The math behind it is really actually quite fascinating if you're interested in looking into it. I got this implementation out of this book here, Handbook of Linear Algebra, edited by Leslie Hogben. Anyway, but it's an iterative solver. Again, finds a solution to AX equals B. And you, being an iterative solver, you have some more arguments that you can pass in. But again, it's generally the same. N is the size of your system, A is your system matrix, B is the right-hand side, and X is your solution. And it will run through and iteratively solve the system of equations. From what my experience, GMRes is a little faster than block Jacobi or block successive over relaxation. But you can tweak block Jacobi and block successive over relaxation more, again, because you can fiddle with the relaxation parameter and the block size. GMRes doesn't have anything like that. It's kind of, it's already optimized, and so you can't do much more to it. With all of these iterative ones, you've got a termination tolerance. You've also can tell it to have a maximum number of iterations, which is useful because, you know, if you've got a system matrix where you're not going to be able to drop your residual below, you know, 10 to the negative 8th or whatever, just for whatever reason, how the system is set up, then you don't want it just continually solving because it's not reaching your desired termination tolerance. You want to be able to tell it, okay, if you've tried 1,000 times to get this to converge, just stop and give me what you've got. That's what maxiter is for. You can also give it an output file where it'll put out information for each iteration. So it'll tell you, I'm at this iteration, this is how much of a change I made to the x vector, this is now my residual, and so you can kind of track and see how it's going. And total iter is also a variable. This is a result from the subroutine. Total iter will tell you how many iterations it actually ran. And so you can know, without having to go consult this output file, how many iterations were run by the solver in finding your solution. I'll point out this last one, but I don't think it'll be used all that much. You can restart GMRes, and that's because a lot of implementations of GMRes require more memory and more computation time with each iteration. So as the iterations proceed, the computation power and the memory requirements go up. And so often what's done is you run GMRes for 20, 50 iterations, and then you say, okay, I'm going to take that solution, the vector that I've gotten to, and start over with that. And so you can plug that back in and run it again. I've found it doesn't do much for improving speed or final accuracy. It's really just a matter of memory. But the way I've got things implemented here, again, I don't see that being used too much. So that's a really basic introduction to this linear algebra module. I hope that helps. I hope that also helps with just seeing some real Fortran code. This is what it looks like. We've done some really basic stuff in the demo so far, but this is the real deal. Anyway, I hope you enjoy it. Leave questions in the comments, and yeah, I'll probably be creating more videos to come.